Okay, so welcome back to part 3, and in this video we're actually going to be talking about the adiabatic saturation temperature and how it relates to the wet bulb temperature and the stuff that we've been talking about in the past few videos. Um, so, oh, okay. So actually, before we start on that, I did make a mistake in the last video, which was right here. This density, I forgot to include here the molecular weight. So we're going to need to include that there, here, here, and actually what we'll end up doing is that should be included here. And I also forgot to bring down this CP. So that would go here as well. Okay, so we have that, our energy balance with a few corrections. Okay, and then from there we're actually going to move on to the adiabatic saturation temperature. So the adiabatic saturation temperature, we're going to set up a scenario here where we have a long pipe, and we can assume that this is going to be an infinitely long pipe, and it's going to be insulated, hence the name adiabatic. Okay, and actually what we'll do is inside here we're going to have some water at the bottom. And this water, well, we're going to have air going through the pipe. And this air is going to go through the pipe, and it's going to become the water from that's already inside the pipe will end up evaporating into the air. Now this water is going to be at the temperature, we'll call it TW. But if we were actually to run this experiment in real life, we would actually control how much, well, we would control the temperature of the water, because we would have to be continuously adding water to the pipe, because as it gets evaporated, eventually the pipe would run dry, so we would have to be adding water. And what we would do is we would measure the air that's coming out of the pipe here. So here this would be, we'll call it T1, and this will be T2. We will measure the air coming out of the pipe. We will measure what T2 is, and we will slowly add in water at increasingly temperatures that are getting increasingly closer to this T2. So eventually our TW would equal T2. So we have that there, and then this air that's actually coming into the pipe, it would have partial pressure of water. We'll call this 1. This will be 1 over here, and this will be 2 over here. This will actually be equal to the atmospheric relative humidity. So this is air coming in from the atmosphere that contains a certain amount of water inside of the air. So that's what this partial pressure of water at 1 is. And then for over here, we're going to have partial pressure of water at 2. And something we want to consider here for this is that when this air is leaving, it will be saturated with water, and the amount of water that's actually in the air is going to be equal to the saturation pressure of the water at TW. And we know TW is equal to T2. So what we can write is this equals the saturation pressure of water at T2. Because again, we're putting in water at TW equals T2. We're putting in water at T2. And that water has a certain saturation pressure. And once, as water gets evaporated into the air, eventually, when the air is saturated, it will have, when the air has a lot of water vapor in it, eventually it will reach the same partial pressure of water as the vapor pressure of the water that we're adding in. So that is why we can make this statement here. So actually the next step for this is going to be to make an energy balance. And we're going to do this by writing down what the enthalpy going in is and what the enthalpy coming out is in order to create an expression that relates the two. So we're going to do an energy balance. So we're going to start here with what is going in. So we know that we have a certain mass here that's going in, and we'll say that this is going to be in kilograms. So this is going to be our mass of air and water that's going in, because remember this air has some partial pressure of water inside of it. And we know that we're going to need the heat capacity of the air. And that heat capacity of the air is going to be multiplied by a temperature change. So the temperature of the water of the air going in is going to be T1. And what we're going to do is compare it to some reference temperature. We're going to call that Tref for reference. And a way that we're going to simplify this problem a little bit is we're going to say that the reference temperature is 0. So for our enthalpy in and enthalpy out, the reference temperature is going to be 0. So I'm just going to go ahead and rewrite this here. So this is the heat capacity times the temperature of the air going in. So this is the enthalpy change in the air, or that's the enthalpy of the air going in. But something we also need to consider is that as water evaporates, there is also an enthalpy change that comes with that. Water, as it evaporates, it adds a certain amount of enthalpy to the air. So what we're going to need to do is we're going to need to come up with a way to write that down as an equation. So the first thing we need to know is what is the partial pressure of water in the air. We need to know the partial pressure of water in the air. We need to know what's going in. So this is going to be the partial pressure of water at state 1, or before it goes in. And we're actually going to multiply this by the molecular weight divided by RT. And what this actually is this is going to be a mass of water. So we'll just say this is kilograms of water divided by, this is going to be a volume of total air that's actually going in. And when I say total air, I mean total air plus whatever water it brought in with it. That's in the air. So this is going to be, we'll call this meters cubed of total. But remember, we have this mass of air coming in, so we need to relate how much mass of water is in the air to the mass of air. Does that make sense? We're trying to relate the mass of water that's coming in to the mass of air that's coming in. And right now what we have here is the mass of water coming in to the mass, or to the volume of everything, but we only want air. So we're going to need to multiply this by, I like to think of it as a conversion factor almost. Maybe not exactly, but we're going to kind of just set up the reverse of this. So we'll have the pressure of total and the average molecular weight. So what this is this is going to be volume of everything again, divided by, and this is actually going to be kilograms of air. I think I might have made a mistake here. So the way I explain this m dot, this represents everything that's coming in. So this includes air and whatever water is inside of the air. So when we have, when we have this here, kilograms of water over the kilograms of water that's coming in over the total volume of everything, what we actually want is kilograms of everything rather than volume. So what this does is this gives us our volume of everything over our kilograms of everything. So this is everything, not just air, which lets us relate our kilograms of everything that's coming in. And then down here we have, again, kilograms of everything. So there we go. And we can actually cancel these here. And what we're left with is enthalpy in equals the mass that's going in times the enthalpy change of the air plus and then this term over here is going to be our enthalpy due to, well, it will represent our enthalpy change due to evaporation of water. Okay. So now we're going to do enthalpy out. And this is actually really nice because it is actually going to be the same thing. There's going to be one difference, well, two differences. So instead of using T1, we're actually going to be using T2, which is the exit temperature. And we would do T2 minus the reference temperature, but remember our reference temperature is 0, so I'm just going to write this as T2. And we're gonna have this enthalpy change due to evaporation again. But instead of the partial pressure of water at 1, we're going to do the partial pressure of water at 2. And if you remember, we said that that's equal to the saturation pressure of water at T2. So I'm going to go ahead and write that. Times the molecular weight divided by total and the average. Okay. So now what we're going to do is I think I might have made a mistake. Aha. Okay. Just a small mistake. So when we're talking about the vaporization of water, or the evaporation of water, whatever, we actually need to include the heat of vaporization. So I just forgot to include that. So I'll be there, and there. Okay. And that relates our how much water is evaporated to the heat, or the change in enthalpy that's required to actually evaporate that water. Okay, so now what we're going to do is we're going to set these equal, because the enthalpy in equals the enthalpy out. So what we're going to say is the enthalpy out. I'm just going to go ahead and copy this down. So the enthalpy out is equal to the enthalpy in. And that would be partial pressure of water at 1 times molecular weight divided by total times the average molecular weight. Okay. Now we're going to need to simplify this as much as we can here. We can cancel these. I'm going to go ahead and move some terms around. So what we'll have here is we will have this term here, partial pressure at 1 divided by the total pressure times the average molecular weight. And from there we will subtract what is in the enthalpy out. And that is equal to this T2 minus T1. And we can actually factor out that. So what we will have is something that looks like this. Where we have the partial pressure of water at 1 minus the partial pressure of water at 2, which is the saturation pressure at T2, equals this heat capacity times T2 minus T1. Okay, and this is our energy balance from our adiabatic saturation temperature situation. Okay, so we will okay, and let's see if I can do this. We want to compare that to this up here. Aha, here we go. move that down. Okay. Perfect. Okay, so this is from the adiabatic saturation temperature, and this is from our energy balance. So, what we want to do here is we are actually going to manipulate this equation slightly, and something we actually want to, I guess, consider is that depending on our units, if we're working with kilograms or working with moles, we would have a molecular weight factor in here in order to convert to a mass from a mole. It just depends on what units we're working with. So in order to keep our units the same, we will say that they're both in moles, or we will say that this is in moles so that it will be converted to kilograms using the molecular weight. So yeah. And what I'm going to do is I'm going to divide by the this total pressure and average molecular weight. And here we have our saturation pressure of water at the surface. And then that equals the heat capacity times our difference in temperature. So what we can see here is that these are actually very similar. Where we have this set of terms out here is exactly the same. And in here we have our two saturation pressures of water. And these are actually flipped. But that must mean these are flipped as well. So actually what we should do is comparing our adiabatic saturation temperature example to our wet bulb thermometers. So this state 1 over here is going to be just the environmental air that's coming in from the environment. It does not have, it's not saturated. There's the only water that's in it is the water from the relative humidity. So in the case of our thermometers, that would correspond to it would correspond to the environment, or what we referred to as infinity. So we could say that this is equal to the partial pressure of water in the environment. So that would mean this is the temperature of water in the environment, and this is the temperature of water at the surface, or at our wet thermometer wrapped in wet cloth. So then same thing here. This is going to be the saturation pressure of water at, rather than T2, that's the temperature of the surface. So now that we've kind of changed these from 1 and 2 to environment and surface, we can see that these are flipped here, but they're also flipped here. So these are actually the same, and we can actually rewrite these well. We can actually rewrite this like this. Equals, and then we will flip this one as well. So again, this is exactly the same thing as what's up here. And what this means is the temperature that we're reading on our wetted thermometer it's the same thing as the adiabatic saturation temperature. So this T2 over here is the same thing as our wet bulb temperature. So finally, well, we've already done most of the work here. So now actually if we were going to actually do this in real life, these values here, this is stuff we would already know or stuff we could look up. Heat of vaporization of water, the molecular weight of water, the total pressure, and the average molecular weight. This one might be a little bit more tricky, but air that has water in it is mostly air, and it would be very close to 29. So we could probably round a little bit on this one. We wouldn't have to be too specific. Now this saturation pressure of water at the surface, and this is actually just to be more specific, the temperature of the surface. We would use the temperature that we're reading on our wetted thermometer, and we would use something like an Antoine equation in order to calculate what this is. The heat capacity of air, we know what that is. We could find that. But something to consider actually would be that as water is evaporated into the air, this would change, and it would, but for the purposes of our experiment, we would just assume that it does not change, and it probably would be a good enough assumption to get us a relatively correct answer. So we will assume that this does not change. And then the temperature of the surface, that would come from our wet thermometer. And this temperature of the environment would come from our dry thermometer. So the only thing we have is this partial pressure of, again, I'm gonna be a little more specific here, partial pressure of water at infinity or in the environment. That's actually what we're solving for. So this is the only thing we don't know. So we would solve for that, and finally, all that's left is going to be to get relative humidity. So relative humidity, and that's going to be this value here, divided by the saturation pressure of water at the temperature of the environment. And again, we would use an Antoine equation for this. And that would give us our relative humidity. So that is it. That is how we would use transport heat and mass transport in order to find and calculate the relative humidity. So just going back over this briefly, we talked about analogies between heat and mass transfer, and from that we were actually able to relate the Sherwood and the Nusselt numbers into something called a Lewis number, which we found that the Lewis number for moist air is actually 1, and because of that we can say that the Lewis relation means that the ratio of the mass transport coefficient to the heat transport coefficient is actually 1 over the volumetric heat capacity. And using this Lewis relation, we were able to set up a energy balance that relates the mass transport, the evaporation of the water, to the heat flux from the air. And after that, we looked at the adiabatic saturation temperature and we did an energy balance on that. And from that energy balance of enthalpy in equals enthalpy out, we were able to find that from that adiabatic saturation temperature, that is actually the energy balance from that gives us the same exact equation as the energy balance we did up here, which was the mass transport equals the heat transport. And they give us the exact same answer, which was a very cool thing to see. So there we have it, the relative humidity. Thank you everyone for watching, and I will see you in the next video.